Okay, so I want to introduce you all to what most people would say is the most beautiful math identity or equation. I'll use the word identity because it's more fancy. It's the most beautiful math identity or most beautiful math equation, and we're going to basically prove that result using what we have learned with Taylor series. So we can get to the most beautiful math identity with our knowledge of Taylor and Maclaurin series. And I'm not going to show you what this result is, maybe you already know, but you're probably interested in how to get there in the first place, right? It's not good enough, I would say, to just know the most beautiful math identity. I find it even more interesting to go to, to find how to get to there, or be able to get to there, because formulas are just okay, that's cool, but how did you get there in the first place? And that's what I'm going to do in this video. We're going to prove using Taylor series. How do I do that? Okay. How do I do that? Let's begin. I want to start with something that we've talked about in one of my previous videos, the Maclaurin series for e to the x. E to the x. So let me just write it. If you don't remember what it is, you should watch the video to see how to get there. So we have e to the x is equal to 1 plus x squared divided by 2 factorial, and I'm going to write a couple more terms than I usually will, because you'll see what will happen later. I'm going to go all the way to the 6th order. Oops, I already wrote 6. I was thinking about 6, but there we go. I forgot the 5, but there we go. I have the first 7 terms, or the 6th order of e to the x, but I'm just going to put ... to show that it's the whole entire parts. So x to the 7th, 7 factorial, plus x to the 8th, 8 factorial, divided by 8 factorial. And remember that video also, the other one, where I go from old stuff to new stuff. I'm going to do exactly that. This is the old information, e to the x. We know how to get there already. This is something we should know. We're going to go to something new. But what new thing am I going to go to? I'm going to go to e to the I times x, where I is the imaginary number, the complex number and square root of -1. And that's already weird. We already made our first weird step. I'm raising e to the I power. We never see that ever. We usually never see that ever. In algebra class, we've never seen something raised to an imaginary number. What does it mean to be raised to an imaginary number? I guess we're going to find out right now. What does it mean to be raised to an imaginary number? If I plug in ix to basically e to the x, every time I see an x, I'm going to plug in I to the x. And I'm already going to do a step here. I'm going to distribute this. Here, let me just show you, and then I'm going to do it. So it's going to be like this. So I'm going to distribute this to each of the terms already, and I'm going to do that to all the terms. I squared x squared plus I cubed x cubed divided by 3 factorial plus I to the 4th times x to the 4th plus I to the 5th x to the 5th divided by 5 factorial and I to the 6th x to the 6th divided by 6 factorial, and this goes on forever, right? So I to the 7th times x to the 7th divided by 7 factorial, and then the 8 one and the 9 one and the 10 one. But I'm just going to write this much because if I continued on forever, it would take too long. Okay, so I guess this is what it means to be raised to an imaginary number. It's just that we have to look at the Taylor series, but we can do something even better. We can simplify. Let's simplify. Simplify. What do I mean by simplify? I want to simplify the I terms. Remember when we looked at, imaginary numbers in algebra class, we gave I to be I to the square root of -1, right? That means I squared is equal to -1. I cubed is equal to -I, because we just multiply this by another I, right? And then I to the 4th is equal to 1. And then if we continue this on, I to the 5th is equal to 1 times I, which is I. And then I to the 6th is -1, right? We're continuing this pattern that goes in basically a type of circle, where we're alternating between -1, square root of -1, -1, -I, 1, and then we go over and over and over again. I'm going to actually keep this as I for now, but you know what I is. I is the square root of -1, but for the purpose we're going to keep it as I. Let's simplify this expression, or this expansion. What do we get? We get e to the ix is equal to 1 plus ix, okay, very cool, I squared, which is -1, so plus -x squared divided by 2 factorial. I cubed is -I, so it's going to be plus -ix cubed divided by 3 factorial. Plus I4 is 1, so it's going to be positive x to the 4th divided by 4 factorial. I to the 5th is I, so it would be I x to the 5th divided by 5 factorial, and I to the 6th. -1, or it is -1, so -x to the 6th divided by 6 factorial, and if I were to continue this on forever, you would just have to fill in all the parts, right? But I'm going to stop here, because if not, I'm going to write a bunch and it's going to waste a bunch of time. I simplified. I can do even better. I'm going to group all the terms that are real, or the terms that don't have I together, and then group all the terms that have I or are imaginary. So let's do that. I'm going to write the real part in red. So we have 1, and this one, and this one, and this one. Every other term is without an I, so I'm going to group those together. And this goes on to forever, right? There's going to be an x to the 8th divided by 8 factorial, and x to the 10th, or minus x to the 10th divided by 10 factorial, and these are all the real parts combined into one group. And then I'm going to take the imaginary part, which I'll write in this blue color. So we have this, this, and this. So we have I to the x, or I times x, sorry, I to the I times x, ix cubed divided by 3 factorial, and ix5 divided by 5 factorial, and I can continue on here, right? It goes on forever. There's going to be the next term would be minus ix to the 7th divided by 7 factorial, and we can continue on forever. So we have this grouped into its real and imaginary parts. I can make the imaginary part better by taking out an I from each term. Since they all have an I in common, I just factor out an I. So this is going to be the same as this, right? Plus dot dot dot, so it's going to be minus 7 x to the 7th divided by 7 factorial. So now we have this, a real part and an imaginary part, and maybe you see where I'm trying to get at here. I have two different things, one about even powers and one about odd powers. We've actually seen this before. Again, that video with the 6 Maclaurin series you must know. If you don't recognize that, you probably should at this point. Like, you should know what these two are. These two are, in fact, trigonometric ones. This one is sine of x. Or no, sorry, this one's not sine of x. This one is sine of x. This one is cosine of x. Very interesting. I'm going to actually replace it with that. Replace it with those two terms. So let me scroll down even further. E to the ix is equal to cosine of x plus I sine of x. And now we have a weird formula happening here. e to the I x is equal to cosine of x plus I sine of x. This is, I guess, what it means to be raised to an imaginary power, is that it deals with trigonometric parts. That's very weird. Trigonometric parts. We barely see e and the trigonometric parts being related to each other. That's already weird. But this is a cool expression or cool equation, but it's not the identity we're looking for. But we are very close at this point. It tells us exactly what raising something to the I power or the ix power is. It's equal to cosine, a real part, and I sine, an imaginary part. What if I plug in a value of x? We can try that out, right? E to the I, or we can do, for example, e to the 3i is equal to cosine of 3 plus I sine of 3. Very cool, right? But that's not interesting at all. Not really. If I plug in this value, it's actually really interesting. E to the I pi. E to the I pi is equal to cosine of pi plus I sine of pi. And maybe you see where I'm trying to get at here. We can evaluate these now. These are exact values that we know from the unit circle. What do we get? Cosine of pi, -1. Sine of pi, 0. So this whole thing goes to 0. Okay? What do I end up with? I end up with this identity. E to the I pi is equal to -1. So e to the I pi plus 1 is equal to 0. This is the identity we're after. This is the most beautiful, or what people say is the most beautiful math identity, math concept, math anything. This formula here. E to the I pi is equal to -1. Very weird. Why is it weird? We arrived at this equation. E to the I pi plus 1 is equal to 0, and we found this through Taylor series. And I guess this equation is very interesting in its own, being that we relate ei pi to be this, the -1, and when you add 1 to it, it becomes 0. And you have now 5 parts. You have e, you have I, you have pi, you have 1, and you have 0. And I guess there's this two interpretations you can take this. You can take a mathematical interpretation, and you can take a historical interpretation. I like the historical interpretation a lot, more than the mathematical one. Let's begin talking about this historical interpretation. On the right, you have 1 and 0. Historically, cultures had to be able to count stuff, right? How many things are there? And the way to do it is by keep adding 1. 1 plus 1 plus 1 plus 1 to get to 4, right? I have 4 things, and I had to increase by 1. So 1's very important to this equation because it talks about the beginnings of math. 1. You can count to any number from 1 by adding a bunch of 1's. 0 is also pretty important historically because not many cultures actually featured a 0 in their counting system. Only a few had 0 or had this concept of a 0 in their counting system. And then we get to the left-hand side, ei pi. Let's start with pi first, since pi is pretty cool on its own. Pi is the number that deals with circles, and when I think of circles, I think of the Greeks. The Greeks are a culture that, I guess, talked a lot about geometry. Geometry, about shapes, about circles, aimed for perfection, and they found pi to be a constant that describes circles. So we have a counting number, counting about 0, or a number about 0, and then a geometric number. Now we get to I, which is an algebraic number. We learned about this in algebra class for the very first time, imaginary numbers. are this natural extension from real to more broader types of numbers, real to imaginary in fact. Every single real number can be captured within the set of imaginary numbers, or complex numbers I should say. And that's pretty interesting too, algebra. This is an algebraic number. And then we have e, which is kind of an algebraic number on its own too. It's also more of a calculus, in my opinion, a calculus type of number, because the way it was actually defined, or the way I like to define e, is this limit. E is equal to this limit of as n approaches infinity of 1 plus 1 over n all raised to the n power. And this idea of limit is calculus, so I kind of think of e as a calculus number. It's also a calculus number because it's a very interesting number. E to the x is equal to e to the x. So we have a counting number, a zero number, a geometric number, an algebraic number, and a calculus number, all wrapped up into one statement. I guess that's what makes it pretty interesting, or pretty beautiful. That's why people probably put it up so high. And then there's that mathematical interpretation that makes it very, very cool. An irrational number, such as e and pi, being raised to the irrational number, well, times I, right? Number, that's not how you spell number, there we go. Number times I is equal to -1 right here. That's weird, irrational times an irrational is equal to -1. And also another part is that you barely ever see something raised to the ith power, right? Imagine what like this would be. That's very weird. This is even weirder because it's the irrational part plus the I, and that's what makes it beautiful in the mathematical perspective. But I would say it's more beautiful in the historical perspective because it wraps together so many things together, so many cultures into one statement. And this is the identity. We proved it with a Taylor series, which is very cool. And I guess the final thing I have to say is, what is this thing called? It must be named something. It is. It's called Euler. Euler's identity. Euler's identity wraps up these 5 different things together. And I guess I'll zoom out just to show you everything at once. We went through this process of learning about Taylor series from the very beginning, and this is one of the things, the power of the Taylor series. It leads us to the most beautiful math identity there is. That is Euler's identity. And we use the fact that we can use the Maclaurin series for e to the x, change it to e to the ix, and then we get this. This is already pretty cool also. This is already a cool statement, but then we make it even cooler by letting x to be equal to pi. And then we get to his identity. So, I guess that wraps up this video. It's not really like required for like a calculus class, but I thought it was pretty interesting to know. And the first time I saw this was a very cool process. I remember watching a video on doing this process, someone doing this process from the beginning, and it was just like pretty mind-blowing the first time you see it, because you never realize how stuff works, and this is an example of how we can get to an end result from basic principles. Because this formula here, this identity, is pretty cool on its own, but I think the process to get there is even cooler. So, that wraps up this video on the most beautiful math identity.